Hello, Professor Simmons here. We're going to look at the theory of how to solve a second-order linear differential equation with constant coefficients that has a right-hand side equals to 0. So here's an example of such an equation: y double prime plus a constant a times y prime plus another constant b times y equals 0. We talked in class about what the form of the solution is, what that means, and what some examples are of using that form of the solution. This is showing why that's the solution. So, to begin, let's think of the derivative with respect to x as a differential operator and call it d. And then we can think that this ordinary differential equation we've written is actually a quadratic in d that's acting on y. Conceptually, that would allow us to factor it into the product of two different linear terms, because you can factor a quadratic polynomial into a pair of linears. But in this case, that would mean breaking down our second-order differential equation into a pair of related first-order differential equations. But those are much easier to solve. So let's see how it works out in practice. So we rewrite our differential equation as this operator, d squared plus ad plus b, acting on y equals 0. So far, all we've done is change notation because conceptually we think it will help us. But think about it. If the quadratic r squared plus ar plus b equals 0 has roots r1 and r2, and those roots would follow the usual rules that you get by using the quadratic formula, right? You'd have the sum of them would equal minus this coefficient a, and the product would equal this coefficient b. So those roots r1 and r2 then should apply in this case as well. That is, we should be able to factor this quadratic into this product of linear terms, d minus r1 times d minus r2 acting on y equaling 0. So conceptually, we've broken our second-order differential equation into a product of first-order differential factors. Now, to make use of that, let's call this d minus r2 acting on y by the name f of x for short. And that means that what we're looking at for this equation is now this shortened verb, this shortened form, d minus r1 acting on f of x equals 0. Let's think about that. That's just df by dx minus r1f equals 0. That's a kind of differential equation we know how to solve for f. So that's kind of interesting, and we'll continue this on the next slide. So let's recap. We've taken our second-order linear differential equation in y, factored it into this form, noted that we're going to call d minus r2 acting on y by the shorthand f of x. And so our full differential equation now looks like this. But if we write that out a little bit more explicitly, we realize it's actually a separable first-order differential equation. We can put the f's on one side, we can put the x's on the other, integrate both sides, add an integration constant, and we find that f of x is an exponential with a constant coefficient that we'll call a hat. Now let's undo the shorthand and get back to saying, d minus r2 acting on y equals f of x. That was our shorthand. But we found f of x, and d minus r2 acting on y is precisely one derivative of y minus r2 multiplied by y. So this is just a linear first-order differential equation. Here's the p factor, here's the q factor. It's in standard form. That's how we knew those were p and q. We know how to solve this because we've already done that. So to find the integrating factor, we need to say that I is going to be the integral of negative R2 dx, so that's just negative R2 times x, and we can solve this differential equation for y. So we know how to write out the solution is simply y is e to the R2x, that's 1 over the integrating factor, times the integral of the integrating factor times q dx, plus we have to remember to add in the extra factor of another constant times 1 over the integrating factor. At this point, there are two possibilities. Either R1 and R2 are not the same, or they are. If they are not the same, then we proceed as over here on the left-hand side, and we say, great, the R1 and R2 and the exponential inside the integral, they don't cancel each other out. So we simply do the integral and get a factor of 1 over R1 minus R2 in our coefficient. Then the exponential factor remains. We multiply it by this other exponential that was lurking outside the integral. And so that's the first term in the answer. We still have, of course, the second term coming along for the ride. And now we see the full answer is a constant times e to the R1x plus a different constant e to the R2x. But if R1 and R2 are actually identical, then we notice that the R1 and the negative R2 here in our exponential will actually cancel one another out, and our integral will be simpler. It'll be a e to the R2x is the factor outside, a hat e to the R2x. The integral is simply an integral over dx, which yields x. So, and we still have the extra term from the other integrating factor coming along for the ride, and so the full answer is now a hat x plus b, both multiplied by the same exponential factor involving that one identical root. So we see from first principles we've worked through, and we've found that we can indeed solve the second order linear differential equation with constant coefficients with 0 on the right hand side, and the form is exactly as we said it would be in class. That's all.